We need to add all those 4 vectors. How to write it in terms of matrix? 2, 3, 3, 4, 1, 0. Okay? You add them and you divide by this. How to write it in terms of matrix equations, please? This is, we call it x, right?
Yes.
So how to find mu, please? So mu should be 2 coordinate, right? Okay, so what we do here, please, if we take x, t, transpose, which would be the line, right? And we multiply by 1, 1, and you divide by 4. Same thing, right? You okay with that? Because how it will be here? In matrix square, it will be my x1, x2, x3, x4. This is why I put a transpose in order to change it to column. This column here, if you multiply it by 1, 1, 1, 1, what should be? You add in the first coordinate, divide by 4. You add the second coordinate, divide by 4. So to write it in terms of matrices, okay? You can check it, it's the same thing. So what is the next step later on? What we do after finding the mean? Okay. We have to find the covariance matrix. What is the covariance matrix, please? So the dimension should be what, please? Dimension of the covariance matrix.
N by N. N by N. No, M by N.
M by N, which means 2 by 2 by 2, right? So what will be here, please? Sorry. What is x here? 2. So I have to put x transpose, right? Minus, and here x. Do you agree with that? We have to subtract the mean, right? But how to find the mean? I need to repeat it for every xt here, right? So xt here. So the new x, if you want, we have to subtract from the x1 the mean 4 times. Yes. So what will be here, please? Minus mean. But I have to repeat it 4 times.
4
yes?
times.
How we carry this one as a matrix?
Multiply by 1.
So this one, how can be written? To find the mean have to repeat it 4 times. Here the mean 2 by 2. I think should be the mean multiplied by 1, right? Clear the idea? Yes, exactly. Okay. So what will be here, please? Just a second. Here what will be x? It will be minus the mean times 1
cross 4.
transpose. And this is minus mu 1 transpose. And here I can put it x is xt, exactly. So when you do the covariance of this, it is, when you do the calculation, we get our covariance matrix. Okay? Is the same question? Just a second. Okay, different one. Okay? So just calculation, right? Is it clear for all? So when you find the covariance matrix, what we need to do next? Eigenvalue and eigenvector, right? So here a matrix, what should be here? Matrix should be something A, B, B, because it's symmetric matrix, right? Correct. So this one we can find eigenvalue and eigenvectors. So what should be the matrix, please? It will be P transpose times diagonal, right? Times another, here we call it the first eigenvector and the second, let me call it like this, V1 and V2. But this just we call it the matrix P. And what is the P transpose? It will be V1 transpose, V2 transpose. So you have lambda 1, you have lambda 2. Imagine for example here, just I'm not doing the calculation at the end, you can do it. Imagine here we have for example 1 and here we have 3, just for example, right? What will be the main direction? in this one? Is it V1 or V2? Which one? V1 or V2, please? V2, because
V2.
this is to the first one and this to the second one. So the main one, what will be? V2. So how to find eigenvalue or eigenvector? Please, you can do it, okay? Hear the idea? So everything is in lectures note, I just put it again here. But those techniques, try to understand how you can use it, okay? It's really to facilitate your way of writing things.
So, Doctor, in the question, which PCA algorithm would you choose?
Okay, compound the unit length of the principle of it. Which one of the PCA algorithm would you choose if you request just one? Yes. If you want to do only one principal compound, which one you will choose? The biggest one.
The biggest.
Yes, as simple. So I say example here. If you have 1 and 3, so here you choose V2.
No, I mean, what is the algorithm again?
Okay, compute the unit length, principal component, direction of x. What does mean unit length? Yeah, the modulo of the function should be 1. So what does mean here? When we do the eigenvalue, eigenvector, we have to make sure always that V1 is equals to V2 and equals to 1. Should be a unit vector. Okay?
Yeah, absolutely.
And after state which PCA algorithm would you choose if you request to just one. So here just we do only one because we didn't do too much of the variant. Okay, please provide exact answer, approximate, show your work. Okay, for example here, if I choose now only one V2, yes, what should be my new data? What is it? So every x1, x2, x3, I will do the projection on V2. Look at please. What should be here, please? I have 4 data: x1, x2, x3, x4. I will do the projection only on V2. So I get a new coordinate, right? What should be the coordinate here, please? Who can tell me? V2 transpose x1. V2 transpose times x2 until the last one, right? How we can write this one here, please?
We take out.
U2 transpose times x, we call it x transpose, and we are done. Here we get the new, only one dimension, right? Clear? Because this is value, right? 1 value, 2 value, 4 values. Yes? Is it clear here or not? Okay. So why we are finding V2? To do what? Because the data will be represented only on the direction of V2. So any x1, x2, I have to do the projection on this direction of V2. How we do the orthogonal projection? Let me remind you. When you have any vector like this, x, and I want to do the projection on the unit vector u, what should be here the direction, please? The value here, please? The distance here. Is u times x, direction. So exactly, x1, x2, x3, x4. From my old basis, I'm going to the base of V2. So what I do, x1 projection on V2, x2 projection on U2, and so on. So why we do the eigenvectors? In order to do the projection on those directions. Yes?
So why is it not x1 V transpose? And,
Okay, good question. You mean you want to say why we don't do x1 transpose U2? Which is correct, listen.
x1 multiplied by V2 transpose.
X1, yes, sorry, this is V, sorry. Oh, sorry, yes. This is all is V, this is V, thank you so much. Yeah. No, it's like V, yeah, thanks. Here we can put X, yes, X times V, yes. Yeah, yes, thank you, yeah.
It's very fast.
Sorry?
I cannot get it.
Okay, why we do PCA, please? Okay, tell me why. Let's summarize again. We do PCA to look to the data in different bases. Clear? So those bases, it is important. Why? Because some lambda is 0. What does it mean? Lambda is small, means the variance of the data in this direction is small. So there is no variation. I can't cancel it. So we do all the calculation here. We find V1 and V2. Take example here, lambda 1 is 1 and here is 3. So the data is more changing or more variable on the direction V2. So I can compress my data only on the direction of V2. Look, this is direction V2. You have x1, x2, x3, x4. You do the orthogonal projection. What does mean orthogonal projection? Means your directions transpose times your vector. As simple as that. As I'm saying. So now, from the old data in 2 dimension, I'm going to the data of 1 dimension. That's all. Okay. Look, for example here. I do another example. I have these functions here. Here, after when you do the subtractions, you can center your data. We get this one. Okay? So the same one as we did before. So now here, what is the data is centered, right? You can check it. The sum is 0, right? Yes? So here, what is the covariance matrix? 10, 6, 6, 10, right? So here I just put numbers. Now I'm putting the real number. What is the eigenvector here? So please, you do with TA how to find eigenvector. I will not do it again. It's an easy task. Here we have 16 and here we have 4. Look at the eigenvalue 16 and eigenvalue 4. Okay? So the variance in V1 is 4 times higher than V2. Clear? Yes? So what will be my data, please? This is just the mean, I put it here. So what will be your projection now? What we do?
V1.
X1, we have it. X2, we have it. X4, we have it, right? They are here. X1, X2, X3, X4. You put it in column here. V2, what is V2 here? 1 after square root of 2, 1 after square root of 2. When you do here, you get the projection. You get a new value. I don't know if it is here or not. Not here. Now let's get calculated together, please. What will be here, please? What will be the value here, please? What is V2? I can take V2 can take 1 out of square root outside. So it will be here 1 times. What is x1, please? 1 minus 1, right? Next one, what is it, please? 1 square root of 2, 1, 1. What is x2? Minus 1 and 1. Do the calculation here, please. What will be here? 1 minus 1 is 0, right? Yes? Second one is 0. Let's do the third one. 1, 1. It will be 2, 2 is 4. Last one is minus 4 after square root of 2. You see? I compress it from matrix 2 by 4 to 1. And 2 of them are 0. Okay?
It should be 3.
Sorry?
The third value should be 3 by square root 2.
The third one?
Yes.
1, 1 times 2, 2. What is it? 4. Okay? Yeah, because x3 is 2, 2. x4 is minus 2 minus 2. Clear? So what does it mean? Instead of using the matrix like this, you can deal only with this. Is it clear for all? Try this one here. So I do a few, but I cannot do all of them. You can do it with the TA more. Look, for example, here. Draw the principal component here on the projection. Just as you can guess, what will be your principal component? Now we have to do it geometrically without doing the calculation. So give me a direction where the variance is bigger. Do you think, okay, do you think can be any direction? Yeah, I want to see a line when I do the projection, it should be the range is bigger, as much as you can, right? So we can say is this one, right?
Yeah, that's
Yes, excellent, yeah. So we can say here, let's try if it's correct or not, right? My data is this one or not? What is the first one? Look, is 1, 0. Second one is 2, 3, 4, 1, and 5, 4. I put it here, right? This is my data here. Let's try to calculate the principal component, right? The data, is it centered? No, right?
No.
So what you have to do, to find the mean, you subtract, you calculate the covariance matrix, and you find the eigenvalue and the eigenvectors, okay? So the principal component here, I did just, so now it became easy way to do the calculation. Not easy, but the way algorithm is clear, right? And we find here, so at the end what we get here, please? yi, the coordinate is this one. So what we do, you multiply your principal component by it. And you can see here, the 4 coordinate will be only those points here, right? Okay? And here we can say, what is V1 here? Is 1, 1, right? But 1, 1, it is not unit. For example here, if I ask you, can you, without any calculation here, can you give me V1 here, please? The principal component. Sorry. This one. We can say is 1, 1, right? If you say 1, 1, it is wrong. Who can tell me why it is wrong? It should be unit vector, please. When you say 1, 1, you have to divide it by the norm, please. It's very important. For example, according to the geometric guessing, we can say V1 is 1, 1. But what is the norm here of V1, please? What is the norm? It's square root of 2. So we cannot, right? So what we do? How to make it unit vector? We divide, so it will be square root of 2 of 1, 1. Clear? And it's the same thing, you put it like this, huh? 1 square root of 2, 1 of square root of 2. And you do the calculation. Here, I'll let you do it at home. So we do it later on. Is another question I want to solve? Just a second. Okay, let's do another questions here, please. So we have three data, right? So what is here M? If I ask you what is number of features here? 3, yes. And the number of samples is 3. It's easy. Okay. Can you please compute the kernel matrix for the Gaussian kernel, assuming sigma is 0.1? Can you try? What is the formula for the Gaussian kernel, please? K of xi, xj, what is it, please? Exponential minus 0.1, and here we do the difference, right? Xi, xj. Is it square here, please?
Yes.
It's square, right? So can we find kernel functions here? For all possible ones, right? So what we have, kernel is just you need to calculate the Euclidean distance, and you multiply by 0.1 and then exponentials. Example here, if I want to find k x1, what is it, please? Exponential 0, which is 1. K x2 is equals to k x3, and they are all equals to 1 because the distance between itself is 0. E to the power 0 is 1. Let's do, for example, k x1 with x2. How to do it, please? It will be exponential minus, let's do it like this, exponentials. 0.1 minus, what is the distance x1 and x2 please? It will be 1 square minus 2 square and minus 3 square. So what will be here please? It will be 1 plus minus 1 minus 1, it will be minus 2 square is 4 plus 2 plus it will be 3 plus times 9. So what will be here? Exponential of minus 1.4. Okay? And you can do with the others, same thing. So we can have, what is the size of the matrix kernel? Is n by n. So here 3 by 2. Clear? So we can find this is our matrix, right? And you see here, the diagonal is always 1, 1, 1. And here, can you check this calculator? Exponential to minus 1.4, you will get it is 0.2466.
When we square root, we don't, when we power by 2, we don't square root because it's Euclidean distance, right? We're getting the Euclidean distance.
Yeah, Euclidean, yes, correct. Yeah.
We don't square root everything.
I don't know, here, yeah, but here we put, this is why I ask you, Gaussian, here we have square. So you remove the square root, right? If you don't do square, it will be under square root. Yes.
So the kernel matrix, this is our new data?
What is kernel, please? What is kernel?
It's a function that will transfer our data into a new dimension.
Exactly. So, let me write it, yeah. So, kernel is, this is the target, exactly. So, kernel, look here. Kernel is the dot product in the space of features. For example, phi of xi, xj, this is exactly the kernel. Sorry, I did the wrong thing. No, sorry. This one is when we do the dot product of xi. Okay, when we do the features xi, we multiply it with the feature of xj. Since we don't have this one always explicitly, we write it always in kernel. So the kernel is the dot product in the feature space.
And this is what we did right now, the kernel.
Yeah, exactly. So what is this one here? This is exactly phi of xi times phi of xj. Exactly.
So why the matrix here, the number of features, is the same as
Here,
the
the matrix here, n by n. We don't, number of features in the new space, we cannot find it all the time. Sometimes yes, sometimes no. For example here, it will be infinity. Exponential something, you do Taylor series is, you know Taylor series, right? So it's infinity features. So sometimes it's really difficult to. But we don't need it. Since we have kernel, we don't need it. We don't need to know what is the feature space. So this is the only trick about kernel. This is why. What we can do with this one? We did all the proof. What we need with the kernel functions, the eigenvalue of the covariance matrix in the sample space are exactly the eigenvalue and eigenvector for kernel functions. So this is why the link here, exactly. So instead of doing something I don't know, I use only the kernel one.
Can you repeat?
Okay, so how to find the eigenvalue and eigenvector in kernel PCA? In the normal PCA, we show the example, right? We find the covariance matrix and we do it. But in kernel, we don't have all the time explicitly what is the sample space. We don't have it, sample features. We don't have it. So what we do, instead of calculating directly, we proved it last time, that the eigenvalue and eigenvector, we can find it only from the kernel matrix. Clear. And kernel matrix, we have it. Because any dot product, you have the kernel, and the kernel is given. We use polynomial, we use Gaussian, whatever. Yes?
So later on, when we calculate the eigenvectors and
Yes.
values, we will select the one with the highest
Exactly,
value,
same
and these will be our
directions, yes.
directions.
Exactly, the same idea as we did in the PCA.
Yes, Dr. sometimes K is like a value, sometimes it's, this is confusing.
Because it depends. In this specific case, we are using current exponentials. But there is other case, and within the lectures, we use polynomial. So it is given to you. So we will do a mock exam, we solve it together, and I ask the TA to do more examples on these directions.
Doctor,
Yes,
what is the
I think it's, I don't know, you're dealing with the TA to ask online, to agree. If there is a high, what do you call it, what we did last time?
Agreement.
Agreement. But in terms of, I how to say it? I forgot the name, the log one functions we did. I forgot the name, yeah. Anyway, it's the logarithm H. Entropy. What if the entropy is high? You decide. If the entropy is low, I will do my own decisions. Okay? So it's up to you. Let's do the second one. Compute the norm of H vector, please. So the norm, we have it, right? How to do it, please? For example, here, I want to do the norm. I give you one idea. Okay. Let's look at, try to change the equation, the question to equations. This is really important. What are the questions here, please? Find the norm of some vector in the feature space, yes? Let's take, for example, phi of x1 and phi of x2, yes or no? I put the difference and their distance, right? How to find it? Let's do the square after you put square root, okay? Yes. What does mean vector minus vector? This is vector. Look, vector minus vector. I will get a vector. How to find the distance? By definition, phi of x1 minus phi of x2. I have to multiply, transpose, multiply by itself, yes? Row, column, it gives me value, yes or no? X1, here 1, 1, 2, and here 1. So please tell me, is it clear how changing question to equations? Yes?
I have a question. What is the feature space? Is it the same with the kernel?
Okay, good. Okay, let me review it. I think I did it here. No, not here. It's another one. Okay. Can you clear here? Okay, please. What we have at the beginning, we have x1 until xn, right? We are going to a new space with more features. The features can be handcrafted or can be by using kernel functions. It's up to you. So what will be here? Another functions, another features. Yes? So here features is more richer. So if I want to find the norm of this one, how we can do it? If we have a vector, how to find the norm? Row column. So exactly here. I want to find the distance, mean, vector minus vector. I want to find the norm of it. What is the norm of it? Transpose times this one. Row, column. Yes? Clear or not, please? Just imagine it is kernel is another space with a lot of features. Just imagine like this, okay? You have x1, x2, xn, maybe x1 times x2, maybe x1 squared divided by x3 plus 1, whatever, different combinations. We don't care much.
The norm is x squared plus sigma, right?
No, this is kernel. No, don't confuse. This is kernel functions. I'm coming to it. Just follow me.
This is the difference, like,
Yeah.
not norm, this is the distance. The minus.
Okay, let's go back to normal algebra. 1, 2, 3, 5. 2 vector. Can you find me the length of the distance? Yeah, if you sketch it, what will be here? This minus this. What will be the difference? minus 2 and minus 3, right? What is the length of the distance? 2 square plus 3 square under square root, right? So, what is the problem here? Imagine here, this is a vector, this is a vector. I ask you to find the norm. What we do? Difference, and you do the Euclidean one.
Yeah, I don't understand why we are doing the difference.
What is the difference?
Yeah, because we want the norm of each vector.
No, okay. No, just a question here, I'll tell you why. Just a question said, what will be the norm between x1 and x2? What is the distance?
Yeah, this is a different question.
Yeah, I'm talking about question
B.
B, yes.
B is the norm. It's not the distance.
The norm is the same distance, yeah, same thing. Norm, modulo, the length, the distance, same thing. You see, for example, okay, if you have 2 points here, what is the norm? Could be the norm of each vector. I don't know, sorry, yes, I got your point. Here is C, I'm doing C. I'm sorry, okay, yeah, thank you so much. I'm doing C, thanks. So if we do the norm, what will be the norm? I'm coming to it. What is the norm? B. It will be the norm of x1 squared. What is it, please, here? Phi of xi and 1 transpose times x1 itself. Yes? What is this one here? What is this one? How to calculate it? We don't have the features, right? Here the trick is kernel x1, x1. Yes, exactly. Clear? How to do this one here? Can you think, please, with me? Now, what is the distance? Find the distance matrix. We got it, right? Compute the Bellwether's communication. Okay, for example here, if I want to find the distance between this one, how we do it? This one, right? What's the next step?
Take the
Multiply.
end
You
of
do
the-
this one times this and then this and so on, right? So what should be? Can we do it together? Okay, the transpose here, can you put it inside? Yes, because there's no multiplication. It will be T. So this one times this one, what will be, please? Kernel of x1, right? This times this. Minus kernel of x1, x2. This times this. Minus kernel x2, x1. This times this is
Positive
kernel of
x2,
x2. And we have the kernel, we calculated already, right? So this one here, x1, x2, x2, x1 are the same or not? The same vector. So what will be here, please? I remove this one here. What to put here? Minus 2. Okay? It is here, you can see. Difference 2, 2. And here, what is x? x1 is 1. So 1 plus 1, 2. 2 minus 2, kernel of this. And we get it here. Okay? And you find the matrix from the kernel. And we can do the cosine. We defined last time. Cosine distance is just this over this. And you can find, you put your matrix. And here is different one. You just have to find the mean of it. The mean in the new space you add it. So I not go here, I need to do it with a TA please, because otherwise I can't finish anything. Okay? So please try to do more exercise on the kernel and PCA, okay? So let me summarize it easy way. PCA, what we do, you find the covariance matrix, you find the eigenvalue, eigenvectors. In the kernel, you have to find the kernel matrix, because the covariance, we cannot calculate it directly. So the eigenvalue, the eigenvector are the same like the kernel matrix. And that's it. You find the principal and so on, okay? The calculations in kernel function is always we use kernel, okay? Because we don't need to know explicitly the new space. Because always there is product. Always there is this times this, always the product. So we need only the kernel functions. So this is one. Clear? Okay, so now we go another topic. Yes.
So in the future space, like, you don't care about direction?
Yes, we don't care about how to know them exactly. We don't. But under condition, you have to know the kernel function. So kernel can be polynomial, degree 2, degree 3, can be exponential. You can create your own functions. How to create kernel functions, please? It's a good question. How to create kernel functions, please? You cannot do it randomly because sometimes some functions are not kernel. So how to do it? So by definition, kernel of x and y, you can do it like this. I don't you do it xty divided by xty here plus 3. You can put here power 5, whatever you want. But always keep x and y together. Okay? Do any function you want.
So normally, will you be giving the kernel function or you have
In the exam or in the research? It
the
def-
life?
the level, you have to find some of them. It works. Certain cases.
And
Yeah.
how can we know which one can fit our data?
Honestly, in high
We have so many.
yeah, in high dimension it's very difficult. There is no visualizations. So there is no research. For example, I have a data. I try to do visualization in high dimensions, so you can have some idea. You see, for example, last time when we did circular ellipse, okay, yeah. But if you don't know, you have to try. Yeah, honestly, yeah. Because you don't know in high dimensions. For example, some data they have 20,000 features. How come you can see? You guess it's very difficult, honestly. So this is why we go to the Gaussian, because Gaussian give me infinity of features. Maybe among this we can find the best one. He asked me why exponential gives infinity, please. Okay. What is the formula? What is the formula for the exponential, please? Exponential. Exponentials. Just give you an idea. Exponential of star. Any expression here. It is the sum of from 0 to infinity of star to the power I over I factorial, because it's infinity a lot. So this is why it is not easy to handle. Okay, so let's go now to another way. Now we have a matrix. I will try to deal with it as matrix. I will not go to the covariance matrix or something. Okay, so we call it singular value decomposition. What does it mean? The same matrix, I will try to write it as a sum of different matrices. Okay, but every matrices, it is just product of two vectors. It will be easy to compress it. So I will not go too much in proofs, okay, but to give you a little bit an idea how it works. So to understand deeply, you have to know what does it mean row space, what does it mean column space, and what does it mean rank in linear algebra. I give you the main theorem. Why? I'm giving some proofs here for those who want to dig more on it. Because still, imagine here, SVD, there is no kernel SVD. If you are able to create kernel SVD, it will be new window in research. Okay?
What do you mean by that? What do you mean we don't have
It doesn't exist on, no, still, people they use kernel PCA, SVD, but you link with certain nice kernel with SVD, you do something new direction of research. Okay? So I'm just giving idea how we do it. Okay? So I'll not go to the proof. So usually what is it? Give me eigenvalue. They are all positive. Why it is positive? Because the matrices, we can arrange them to be symmetric. Symmetric, semi-defined positive matrices mean the eigenvalue are always non-negative. Can be 0 or positive, but not negative. So what we do, we call this one singular value. It's just the square root of the eigenvalue. It's just a new definition, okay? So what we do, give me any matrix, your data, I can manage to write it as U sigma V transpose. Sigma is diagonal matrix, but in the diagonal are not eigenvalue, are square root of the eigenvalue. Means they are singular value. The U and the V are eigenvector for certain matrix, and U, they are eigenvalue for the transpose of this matrix. I'm coming to it. Clear? So the way it is a bit different. I'll not go in the proof. This is, you can do it. I prove it from scratch. The most important is here. Okay, look here, please. This is what you need. The oldest one, if you need help, I can help you. I will not give it all the details, but we prove it from A to Z. Look here. You have a matrix A. I will try to manage to find U, sigma, V. What is U, please? It is eigenvalue, eigenvector, sorry. These are the square root of the eigenvalue, and those are also eigenvectors. What they are? Look here. The V are the eigenvector of this matrix, A transpose times A. And this matrix is symmetric or not, please? What do you think? A transpose A. It is symmetric. Why? Why it is symmetric? If I ask you questions. A transpose A. Do this one here. I have to check it if it equals to itself or not. Yes? Yes or no? Okay. Let's work on this one. To do the transpose, when we have the product, we have to change the A, T, what is it? Transpose of the transpose is itself. So the matrix is symmetry. Okay, so eigenvalue of V, we know how to calculate it, right? It is ATA. Now, next one. From the same matrix, I can find the eigenvalue. We put them under square root, we find the singular value. So now, I managed how to find this, and I managed how to find this. Still U. What is U? U is when you get the eigenvector, we have the matrix A, just multiply it, you get another vector. We need to normalize it. You divide it by square root of the eigenvalue, you get your U. Done, finish. So we have U, we have sigma, we have V. Is done. To prove why, go to the 3 previous slides. Clear the idea? So again, we are using the eigenvalue, we are using the eigenvector. So it's really important to do the calculations.
Doctor, what is the summation symbol?
Summation?
Correct.
This one here? This is sigma, this one, right? This sigma. Sigma means diagonal matrix, this one is here. This is our sigma. Everything is 0, 0, 0, except for the diagonal, okay? And diagonal a certain k. What is k is up to, usually when you calculate the eigenvector, eigenvalue, you will find a lot of zeros. Few of them are not.
This sigma 1, sigma 2, we are calculating later?
Yeah, this is how to calculate it. Give me your matrix, your data is A. Yes? How to find all U vectors, how to find the sigma I, lower sigma I, and how to find the V. What is the V? Is only the eigenvector of this matrix. Clear? The sigma is square root of your eigenvalue of the same matrix, this one. Later on, how to find U? Just you put A times the eigenvector, you divide it by sigma. Finish. No. Clear? Is it clear?
The size of the matrix.
The title here, SVD.
No, I mean in which the U covariant matrix and V have sizes M by M, M by M.
You think about size? Okay, what is the size at the end here? We have N here. The size A is M times N. So what will be the size of this one here? Okay, if I ask you here, what is the size of? I have you. What is the size of V here, please? What is the size of V?
N by
What is the size of the matrix V, please?
N by
Why? Let me check. Okay. What is the V? V are the eigenvalue of the matrix ATA. Yes or no? Yes. What is the size of ATA? What is the size of A? Is given M times N. And this when we do the transpose, what will be here? N times. So what will be the end is M by N. So the size of this one is N by N. Why? Now, if we have the size of V, we have the size of sigma. What is sigma here? Is N out of M. Okay? And here the size is M by N. Okay? U is m by m, V is n by m, and the matrix here is m times n.
So sigma, that's supposed to be n by m.
No, this is in the PCA, no, different scenario. Yeah, different scenario, okay? A different scenario. Clear now, please? How to calculate it?
Doctor, the U is with size?
The m by m.
M by M?
M by m.
And the A is N by M.
Yes. Okay, look for example here. We have, sometimes I call it delta or sigma, doesn't matter, okay? So you have U, diagonal matrix times another eigenvector, transpose. But here you have to make sure, both of them, they are orthogonal matrix. U times is a transpose is identity matrix. V times Vi are identity matrix. But you see what you put here? This is M by M, and this is N by N, as we said before. So the size is this way. So what we have here, U, we have the eigenvalue, eigenvectors. V, we have the eigenvectors, and this is our diagonal matrix. So how we are compressing it is in this way. Let's arrange them to biggest to small, as we did before. So if here some of them are small, we can remove them. Okay, so we are compressing the idea. Look, for example, here. Can you please tell me, from the way we did the presentations of the X, this one can be written in this way? Can you or not? Please. So we have, let's say, for example, we have a matrix like this. Look, for example, here. I have a matrix here. Give me a value here. For example, I have U1, and they have U2, U3. Here we have, for example, here 3 by 3. And here we have, for example, 2, 1, 0. So we have 3 by, and here the N, for example, we have transpose, right? V1, V2, V3, V4, for example, right? Okay. And here I have to do another 1, 0, 0, 0, 0, 0, 0, 0. Okay. Look at this one here. If I do the product, how you can calculate? Do this one times this one. What you get? This times this one, we get. What should be here, please? The new matrix here, please. 2 V1, right? After 1 V2. After 0. We don't need it, right? Now, what will be here, please? U1, of course, this is transpose, huh? Okay? U1, U2. So this is the idea here. U1, U2, U3. What will be here, please? This time, this, what will be? 2, U1, V1, plus 1, U2, V2 transpose, right? So what I did here, a matrix, I change it to, this is matrix and this is matrix, right? Because we have column, row, not row, column. So matrix, matrix. What does it mean here? Instead of representing another matrix here, what I need? I need 4 vectors only. So it is compressing, right? It's the way how to compress it. And here we have 0, because everything is 0. All the eigenvalue are 0, doesn't need in calculation. So what will be at the end? I am writing my matrix as small matrices. And those matrices are the product of the eigenvector U with eigenvector V. You see here, U1, V1, transpose, U2, V2, and so on. So now you need all those vectors, but maybe few of them are not important. You see, for example, here, I keep only the R. Anything bigger than R until N are almost 0. So I'm compressing my data. Okay? So we can approximate the matrix to something small matrices. It's like we are adding noise, very, very small noise to it. So you see here, this is important why we do this one, because at the end we can write it as a sum of matrices. Okay?
So, Doctor, that's BD as a way to compress data.
Yes. Yeah. It is I can say it in a different way. I can write my matrix as a sum of few matrices. But every few matrices, it is just a product of two vectors to get it in all. For example here, imagine you have a big matrix. What do you need? You need U1, U2, V1, V2. Just 4 vectors instead of the entire data. Okay?
So that is this compression or selection? Which is
No, compression here. We are compressed here. Because I'm doing just to a decomposition of matrix on another matrices. So it is compression here. Yeah. But feature selection, no, I don't think so. No. Even PCA, well, I'm doing feature selection, by the way. PCA is not. We're coming later on how to do. No, it is not. It is not in classification, no, at all. Let's take example here. I have this matrix here. N is 3, and M is, I think, 5, right? Okay. We try to calculate the eigen. How to calculate V? Yes.
From such matrix, how can we figure out which column is the feature and which column is the data?
Exactly. Here I don't care. This is my X. This is my X. This is my M. This is my N. I do the decompositions. Doesn't matter. So in this case.
But I need to know because eventually I have to multiply them together. I need to know which one is the data point and which one is the feature.
Yeah. Here, why I didn't talk about features, about variance, about things, because it's just, look here, this is good questions. Before we are looking for the feature selections, but SVM, entire image, I can represent it with few memory to get almost the same thing. So I'm not talking about features, I'm not talking about samples. I'm talking about matrix. In order to have all the data, I need just few vectors to generate it closely. Look to me here, you understand. So I'm talking about features and so on, doesn't matter. You give me matrix here, yes? I do the same process that I show you. You will find U, you will find V, you will find the eigenvector. Look at the eigenvalue. We have only 3. And one of them is 0, right? Look, I try to write it as multiplication is this one. You see? My X, the matrix here, what I need, please? I need U1, U2, V1, V2. That's all to generate the entire matrix. Let's try. This is my V2 to V1 and V2. This is my U1 and U2. And try to do the. Try, please, if you have, do you have your laptop here? On Octave, just try to calculate if you find the same thing or not. Or you can do it at home. So, what do you think here, please? Supposedly, what do you think here? This matrix here, you see this matrix here, I can write it only in those products. It is good or it is some insight on that? One of the way, if you have image, it is a matrices, I can remove noise. I can cancel noise from here. Because any noise is small, the eigen value is small. When you remove it, you are cleaning your data. You see, this is one of the way, okay? Or you can add noise to certain images, okay? Let's example here. Let's do another image now. I add a little bit noise to it. I will call it X tilde like this, okay? This I did. I add noise to the original one. Some noise here. I try to apply my SVD. I will get 3, look here, I get 3 eigenvalue or eigenvectors, eigenvalue, sorry. Here's 0.12 because I generate some noise on it. I get this one here. The difference between my origin image and the one with noise, this is the distance between two matrices. We take the maximum, is 0.35. Let's try to find the V2, we find the U2, and we do only, I will cancel this one, see? I take only 2 main components. I will generate this one. And still close to X, to the original X, and still close to the noisy image.
So doctor, you should always consider only 2 vectors.
No. According to your compression here, why I cancel 0.12? Because 0.12 is small compared to the 2 others, okay? If they are the same, you lose a lot of information. But when it is little bit here, you can cancel. Okay? The same way as we did before. But before we are looking for number of features. But here, no, I'm looking for the entire picture, entire image. You get the difference here, please? So, if I ask you what we need to do about PCA, looking at the most important features to represent my data in order to do the classification later on. But here, I have the entire image. I want to compress it, okay? And also we can do it also for the PCA. We can compress image as we did last time, right?
Doctor, can you consider these two new vectors as a new feature here?
Let me think. But those are not. Which feature are you talking about?
I mean, let's say in the first image we had.
Because look at, let's say something. Look at, this is when you do the product. This is a matrix, the same size. So we are not talking about features. You see what I mean?
But
U1, V1 is entire matrix.
yeah, but in that matrix, something represents the feature.
I cannot tell you, honestly, I have to think, I cannot. But I don't think so, honestly I don't think so. Because U1, V1, to generate the entire matrix, no, I don't think so. Yes, here maybe if your image is like features. For example, now precise medicine, you need image, you need data. So the image itself, it is features.
It's not from image. Let's say if it is from, let's say it is categorical data, other kind of data which is the attributes and values record.
Yeah,
And let's say it has like 10 and 20 attributes.
yes.
And we are just trying to find the, select the only two which has most information. So in that case, can we consider it as a feature?
You can, but you have to look to U1 and V1, how they are. Maybe U1 here, there's a lot of zero, here there's a lot of zero. When you do the product, you need only those few. But you have to zoom in. It's not obvious directly. It is not obvious. So here the main idea is writing a matrix as a sum of few simple matrices. But in feature selections, honestly, I don't think so. But let me think about it if I can.
Not feature selection, I mean representing the whole data with few features which are new.
Yeah, of course, yeah. Here, the entire matrix, I have to represent it only by those features, those vectors, nothing else. But those vector does not representing the features here. For example, those are different.
It represents the data.
Yeah, depend on that. Yeah, depend on that. Okay, let's do this one here, please. Can you please try to a simple matrix? Find here. What is the number of features here? If you said 2 is wrong, you said 3 is wrong. We are not in number of features. Here is matrices, please. SVD. You have to be careful, please. Okay? No, here it's all wait. It's yeah, of course. But at the end, it doesn't matter for me. Yeah, it doesn't matter. Yeah, it doesn't matter. You put it like this, or you put transpose, the same thing at the end. It will be the same decomposition. So tell me the process. What is the first thing we need to do? We need to find V and lambda, right? For which matrix? Transpose of this one times itself, right? When you find out everything, how to find U? The matrix, this one, you multiply it by V1, you get U1. The U1, you divide it by square root of lambda 1. This is, and that's it, nothing else.
So why is it like this?
Huh?
Why is it like this? How can
I refer to the 5 slide that before going is, I put all the details step by step.
We cannot.
If you need it, I can help you.
We cannot follow you are saying because we did not yet like ما تشربنا المعلومة تبع last 5 slides.
But this is a different story, honestly, a different topics. A different way. When talking about features, talking is linear algebra, honestly.
Now you said the steps.
No, but later on, after I will finish, maybe after 1 hour and a half, you will do with the TA, you solve a question about PCA and cannabis. Honestly, everything is linear algebra, I'm almost doing nothing.
We mean about the
The steps how to do it, right? Yeah, let's do it here together too. So let me just give the steps 1 second. Okay. For example, here, what we need to do, please, first. So now we suppose you know how to calculate eigenvalue and eigenvector, right? Excellent. Okay. First step, you have to calculate. Let's call this one matrix A, right? It will be A transpose A. Calculate. Second step. Find eigen value and eigen vector of what? Is it clear now? Okay. From this one, what we can find out, please? We can find lambda I. What is it, please? And we can find the matrix V. What is matrix V here? V1, V2 until V. What is the size of this one, please? 2 by 2. Yes or no?
3 by 2.
Are you sure? 3. No, 2 by 2. 2 by 2. Are you sure 2 by 2 or 3 by 3? Huh? No, it is square matrix. Okay, what is the size of this one, please? The size of this one is given. What is it? 3 times 2. What is this one? So what will be the answer? 2 by 2. It's a square matrix. So what we need here? 2 by 2. We need 2. So we need V1. We can calculate it. And we have lambda 1. And we have lambda 2. Clear now? Done, right? Next step. What we need to do? What do you do, please? What is U1, please? Is A V1 divided by V1 divided by square root of lambda 1. What is U2? A V2 divided by. But here, if lambda 1 is not 0, if lambda 2 is 0, I stop. I cannot. Yes? So here we cannot divide it by 0. You agree, right? Yes? Clear?
Doctor, then we also have U2 if it is 0?
I'm coming to this question exactly. If it's not, how to calculate U2? Thanks. So this is the target.
Doctor, in this middle process, how can we say that, how can we choose to not proceed with the just only take
How to? Sorry, come again?
how can we manually choose that we don't have to go lambda 2 and lambda 3 just go on with the down?
But here, when you calculate the eigenvalue, you have the values. And the others are all 0. You stop. No need.
I mean, is there any like scale for choosing?
But lambda 1, you cannot choose. Lambda 1 is coming from the calculation.
Yes, it's something I need to consider.
To consider how to compress, how to cancel it. Yeah, we come into it later. Yeah, don't worry. Yeah, it is like, yes.
Because if lambda is 0, the vectors should be 0, right?
Yes, exactly. So we
We don't really.
yeah, but how to calculate? Look, if lambda is 0, the vector is 0, but how to calculate U2? I'm coming. And usually we don't need it. Usually we don't need it. But sometimes just write it in a nice way. Okay. Clear now, please, here? So, what should be at the end? I have the vector U. I have square root of lambda 1, square root of lambda 2 times V transpose. Finish. Okay? And this one, how we can write it as product? You remember, right? The sum of sigma I U I V I T. That's all. You have U and you have the V. We can do it in the summation. You can write it in terms of matrix product or in terms of this one, small matrix. And the same thing are the same. Let's do the calculation here. Look, I have the matrix ATA, we get 9, 9 minus 9, 9, right? we calculate the eigenvalue, we find 18 and 0. So here we have in the case 0. So this one I cannot calculate it. I have to stop only here. So I have V1 and V2. I have to make sure they are unit vector. Now we have the matrix V. We have the matrix delta. Now we're coming to how to find U1. What is U1? We do A V1, yes, and we do A V2. It's already 0. But here, what is the eigenvalue is 18. So this one needs to be divided by square root of 18 to make sure that is the unit vector. Okay, so we have U1. I divide by square root of 18, which is 3 square root of 2. We get U1 here. So this one is just, look for example here. Just stop it. We have 3D, right? I give you one vector. Can you find the two other vectors that are perpendicular to the system?
From one?
I give you one vector here. How to create another two vectors that form the base? No. Let's give another example. I have in the space here, I give you one vector here. Can you find the one perpendicular to it?
Yes, we
Directly, without easy way. How you can calculate?
product equals 0.
In 2 dimensions, how to do it? I give you A and B. How to find the one it is orthogonal? You flip it and you put minus one of them. You got it? Because the dot product should be 0, right? Look here, 2, 3. I have to find something if I multiply to be 0, right? Orthogonal. 2, 3. Keep it 2, 3. Come here, put it 3, 2, and put minus. So the product is 0. So in 3 dimensions, we have to do we call it, put it here, but I will not go in details. Gram-Smith process, okay? Gram-Smith process, we take this one, we take another one which is perpendicular to it, there is a lot, and after here comes this one, we get the cross product, the one orthogonal to the 2, and we generate. But honestly, I don't need, look at, please, can you tell me here, can I need, those one, I just generate them to give you insight of how to do. But you see here, this one, I don't need it. This one, I don't need it. And those two things, I don't need them. Who can tell me why? Because if you put them and you multiply by zeros, it's useless, right? Look here, take any vector here. This one times this one. So the two last, we don't need them. It's multiplied by 0. So what does it mean? Those, I can remove them. So you don't need to generate other vectors. So what will be your matrix? So this one here, what I want to say, you don't need it. When you are dividing by 0, stop. Keep this one. No need to go forward. So what will be here? 1, 2, 3. So what we are compressing now, we are compressing this matrix by 2 matrices. What are the 2 matrices? Is this one multiplied by this. And this one multiplied. And that one. And you can find your way. Get the idea? Let me check it. I do this one, we stop here, please. Okay. Can you think here, please, about this one? Is to okay. You have U is U1 until UM. I give you V for V1 until Vn. UI and VI as we did in the theorem. So we can generate the matrix A is between this and this. I did it already here by the letter, I answered already. Because when you do the matrix product, we can calculate it to eigenvector product. Okay, the same way. So can you prove this one, the second one? A transpose times UI, you get this one. From this one here. If I give you this one here, please. If I give you this one, can you find out this? Because U are orthogonal matrices. Yes? V are orthogonal matrices. So this one question can be in the exam, something like this. So it is not proof, it is calculations. Look here, please. We have A is sigma 1 U1 V1T plus sigma 2 U2 V2T. That's all right. Look here, please. If I multiply, so what we have, please, here? What we have? Any U I times itself, the norm, if they are different, is 0. Vi and Vj, if we do the transpose, is 0 because they form orthogonal bases. Times itself is 1. So use this information to find sigma Vi. Look here, I want to keep only this and this. What we do? We multiply the both sides by what? By U1 transpose, right? It goes here, and it goes somewhere, right? U1 is 1. U1 with U2, 0, 0, 0 with 0. We cancel everything. So what will be at the end? It will be U1T times A is just sigma 1 V1T. I do it for 1, I do it for 2, for 3, for I. The same way. Okay, so we are doing orthogonal bases to make it easier for us.
We multiply from the left or right side?
From the left. Left. Because why this one is constant, doesn't matter. When it is value, we can take it common factor. It doesn't change. Okay?
Doctor, what does it mean rank A?
The rank?
Yeah, rank A.
Okay, so what I mean, rank in linear algebra? You have space, right? The dimension of the space. You do a matrix, you go into another space, right? In this space, you have dimension of your data, of your input. For example, for R2, we're going to something here. What is the dimension of your arrival data? We call it a rank. Not only. Yeah.
Rank A, it means the same dimension of the A?
No, yeah, is the rank, okay. The rank, if you take the matrix, take the row vector, yes? The row vectors, what is their dimensions? Dimension of them. It is the rank. Or take the row as vector, the dimension of the row equal to the dimension of the column equals to the rank. So is this still linear algebra? I put, by the way, I put the proof of this one, why the rank is so. I put it in the previous slide. So here, we can prove, we have this one here. When you do the products, you get this one, okay? Step by step. This time this is this, other this time this, we get this one. So I prove the first one. We prove the second one. I put all the R zeros, so we just multiply by Vi. So we stop here. Okay? And here we are doing only equations. So those are the most difficult one is PCA, kernel PCA, SVD. Okay? PCA and kernel PCA, we are looking to minimize the number of features, right? And SVD, we are doing decomposition of matrices to the sum of easy matrices. So we are compressing the entire image, right? So maybe sometimes as future, if you can think about kernel SVD, it will be nice. Clear? So for the, if you decide about the exam, we have to decide to take a mock exam, we solve it together to understand step by step, okay? And the mock exam, usually the exam, I give maybe around 140 marks, but if you answer 70, 80 is full marks, okay? So all others are bonuses, okay? So if you answer more, I will put them in the final or in the something else, okay?
Do we usually grade based on the right answer, or do you actually give marks for the steps as well?
I know the idea. I'm more about the concept, not about values. Yeah. The concept. If the idea is correct, I will. Yeah. Okay. But with the lab, it will be the answer. The lab, it will be correct. Okay. So please try to put effort to understand what we are doing. If you have questions, I'm happy to help. Okay.